Hello everyone, I'm Jian Shunggong from Fudan University. It's my pleasure to introduce our ECCV paper here today. This is the teaser of our paper. Rather than focusing on reconstructing 2D feature stimulus, our paper aims to decode 3D stimulus from fMRI signals. In this paper, we propose and for the first time demonstrate the feasibility of the novel task called Reconstruct MinD. We introduced the first large-scale fMRI 3D dataset, fMRI shape, with 14 participants, 14 variance experiment settings. We also present a novel framework, MinD-3D. Now we have shown some examples of our proposed fMRI shape in the left. It conforms significant variance across subjects, surprising differences in object responses, posing a great challenge for out-of-distribution tests. We also show the details in the table right. We compare fMRI shape with existing 2D fMRI datasets. As the first 3D fMRI dataset, fMRI shape features a larger number of participants and frames, providing ample support for experiments in our proposed novel task and further research. We also show part of the objects in the crop part and the APAC set. During sampling, we use Blender to rotate each 3D object into 360 degrees, rendering them into 192 images, which was then compiled into an 8-second video for participants to view. We collect the fMRI data at Zhangjiang International Brain Imaging Center in Shanghai. We firstly collect T1 and T2 data to align fMRI data. We then collect the functional data with a resolution of 2 millimeters isotropic covering the whole brain using a 3T scanner, sampling data every 800 milliseconds. After obtaining the data, we process them using fMRI prep and transform them into 2D images with the resolution of 1024 times 2514, as shown in the figure right. Subsequently, we employed HCP-MFP to select ROIs in the brain for the training of our model. In this paper, we decode the 3D objects only from the fishing region instead of the whole brain. Following this, we resized the ROS into 256 times 256 RGB images. Additionally, we also introduced a 6-second delay when aligning the fMRI signals with their corresponding 3D objects. Now let's take a look at the MinD-3D framework. It consists of 3 stages. In the first stage, we use an UKB pre-trained spatial encoder from LEA to extract features from each fMRI frame, and employ a feature aggregation module to fuse multiple fMRI signals, where each signal represents a free point of the 3D objects. Additionally, we calculate a contrastive loss between fMRI feature and the average clip image feature of K images. In practice, we choose 6 frames for the encoder, and we set K equals to 6. In the second stage, we train a transformer-based diffusion model conditioned on fMRI features to generate fishing features. This diffusion model converts the feature from fMRI space to fishing space. In the last stage, we use the transformer-based 3D generative model Argus as a decoder, adding an adapter every 8 blocks to keep the capacity of the Argus. Finally, we get the 3D mesh of the reconstructed object. As a new task, we define 7 metrics to evaluate our model. We split them into semantic level and structural level. Our method outperforms the baselines in the experiment. It established a new benchmark for the community. Here we present some reconstructed 3D objects alongside their ground truths in 2D renderings. And we also show the result of the out-of-distribution test here. That's all for the introduction. Thank you very much.